In this video, we're looking at functional groups of organic homologous series, considering the different functional groups of organic molecules. Functional groups give characteristic physical and chemical properties to a compound. What is a functional group? Fairly common question. The answer: it's an atom or group of atoms which gives an organic compound its characteristic chemical properties. These are often the most reactive parts of molecules, and my organic molecules are often divided into groups depending on the functional groups they possess. This is because members of the same group will have the same or very similar chemical properties. I've got my functional groups listed here. For me, this little table on the right is more for reference. I would be taking a picture and keeping it for reference. Pointless rote learning all of these. No one will remember them. You get used to them, you get familiar with them by using them as we go through the syllabus. But saying, halogeno contain a halogen, X representing the halogen. Hydroxyl, HYD, R for hydrogen, OX, Y for oxygen, OH group. Very important carbonyl group. A carboxyl group, COOH, acidic. Compounds that contain COOH are carboxylic acids. I've got my ethers, alk, oxy, alk, because a carbon backbone on either side of the molecule is separated by an oxygen, alk, oxy. Amino, based on ammonia, and then the less common, amido, ester, phenol. So I can look at my homologous series, and really I can think of it in terms of bonding. Alkanes, alkenes, alkynes. Alkanes, single bond. Alkenes, double. Alkynes, triple. Examples: the 4-carbon butane for the alkanes, all bonds single. The 2-carbon ethene for my alkenes, and the 2-carbon ethyne for my 3 double bonds. 1 single bond alkanes, double bond alkenes, triple bond alkynes. Alcohols, COH. Pentanol tells me 5 carbons, then the OH. And aldehydes, butanal, it's a C double bond O at the end of a chain. Ketones, C double bond O in the middle. My suffix predictable, coming from the name of the homologous series. Carboxylic acid, COOH, on the end of a chain, oic acid. Then less common, ethers, COC. Amines, amides, esters, halogenoalkanes. Again, I think this, I'd be taking a picture, using it for reference as I approach the different functional groups, different homologous series in organic chemistry. Now, very important. Homologous series is a series of compounds in the same family. They have the same general formula. Beneath, not highlighted, I've explained. The alkanes all fit the general formula CnH2n plus 2. Let's pause with that. If I look at the formula of the 5 alkanes I've got in the table, take any one. Look at the number of carbons. Double it, that's 2n. Add 2, you get the formula of that alkane. Members of the family include methane, ethane, and propane, yeah. So, same general formula. Neighboring members differ from each other by CH2. As I look down the list, every time I go down, I'm adding 1 carbon and 2 hydrogens. Members have very similar chemical properties and show trends in physical properties. I've highlighted that and I'm dwelling on it because I've seen it asked many times. Describe what is meant by a homologous series. Trends in physical properties, look at the boiling points. As the chain gets longer, the boiling point goes up. Density at 20 degrees increases as the chain length goes up. Why is there such a big jump for pentane? There's always a reason. This is at 20 degrees. At 20 degrees, pentane is a liquid, particles much closer together. The gradual increase in boiling point comes from increased London dispersion forces as the molecule lengthens. Intermolecular forces, which are longer if there's simply a larger molecule. Density increases as molar mass increases. A longer chain length makes molecules harder to separate due to increased London dispersion forces. Branching lowers intermolecular forces as molecules cannot be aligned so well. With methylpropane, only 3 carbon atoms can be aligned. I see skeletal structures of butane and methylpropane. Easy to stack the butane molecules, giving them the chance to establish intermolecular forces. Not so with methylpropane. Branching lowers boiling points. Straight chain molecules can line up better and form more London dispersion forces. If functional groups are polar, then stronger intermolecular forces will be established. These could be dipole-dipole forces or the strongest intermolecular forces, hydrogen bonding. I've added this table at the very end, last slide, to show the different types of attraction there could be. Attraction greatest when I have full charge. Electrostatic attraction. At the top, I've got oppositely charged ions, I've got ionic bonding, I've got electrostatic attraction between those oppositely charged ions. This is the strongest force of attraction between particles. Yeah, my particles involved, of course, my oppositely charged ions. Now, if I only have one ion and a polar molecule, of course, the strength of the attraction less. But I do get attraction there. To get this, I would need a polar compound containing, let's say, hydrogen with a slight positive charge attracted to an ion. After this, I get my 3 types of true intermolecular forces, attraction between covalent molecules. Strongest of the 3, hydrogen bonding. Yes, strongest intermolecular force. I have attraction here with a slightly charged hydrogen atom in a polar molecule. 2 polar molecules with a small H delta plus will attract each other. If I've got a small H delta plus as in the diagram in the middle, then I've also got in water an O delta minus. Attraction between the polar molecules ensues. After hydrogen bonding, dipole-dipole. Polar molecules attracting each other, as we see with HCl. It's weak. Hydrogen bonding, much stronger. So for this I need polar molecules, but no H delta plus. London dispersion. All structures can have temporary dipoles because of the random movement of electrons. As we saw before, linear structures line up better. They are more readily form London dispersion forces. But these are the weakest of the 3 types of intermolecular force, and as they're weaker, we only really notice them when I have non-polar compounds. That's it. That completes this video. If you found that useful, please hit like. Please subscribe for more content.